Hello, my name is Garrett Summers. I am a graduate student in the astronomy department at The Ohio State University, and today I will be discussing the key results of a paper I recently wrote in collaboration with Dr. Mark Pinsonneault, entitled A Tale of Two Anomalies, Depletion, Dispersion, and the Connection Between the Stellar Lithium Spread and Inflated Radii on the Pre-Main Sequence. Lithium is an interesting element in astrophysical contexts, as it can be used to trace mixing in stars, infer the ages of clusters, and constrain the chemical yields of Big Bang nucleosynthesis. Lithium is rapidly destroyed at a temperature of 2.5 million Kelvin, which is readily reached in the interiors of stars. Standard stellar models make strong predictions about the magnitude of this depletion on the pre-main sequence as a function of mass and composition. However, it has been known for decades that these predictions are incomplete. In this paper, we have attempted to understand the cause of several discrepancies between observed lithium patterns and theoretical predictions, which I will now discuss. First, standard models failed to predict the median pattern of lithium abundances at the zero-age main sequence in solar analogs. We find that this is most likely related to unidentified systematic errors in the input physics of our models. The rate of lithium destruction during the pre-main sequence is highly sensitive to the temperature at the base of the convection zone, so even a minor change in that temperature can lead to substantial differences in the predicted abundance of a star at the zero-age main sequence. We estimated systematic errors in the various inputs in our models, such as the equation of state tables, opacity tables, and the protosolar abundance, and found that within these errors, our models accurately predict the median lithium pattern of the warm stars in a well-studied near zero-age main sequence cluster, the Pleiades. We use this empirical pattern to constrain the physics in our models, ultimately producing a good prediction for the pre-main sequence depletion in solar analogs. Second, while we have reconciled our models with the warm stars in the Pleiades, there remains a substantial problem in the cool stars. Standard models predict that stars of equal mass and metallicity should destroy the same amount of lithium on the pre-main sequence, but stars cooler than about 5500 Kelvin in the Pleiades show a greater than order of magnitude spread in their surface abundance at fixed temperature. Furthermore, the most lithium-rich stars at a given temperature are also the most rapidly rotating. This implies rapid rotation is somehow able to suppress the efficiency of lithium depletion during the pre-main sequence. In this paper, we argue that this effect is caused by the rapid rotators possessing inflated radii relative to slow rotators. Many rapidly rotating objects, both in eclipsing binaries and in the field, have been shown to possess inflated radii relative to standard predictions. If the most rapidly rotating stars on the pre-main sequence were inflated, the base of the convection zone would be cooled and the rate of lithium destruction would be suppressed. We calculated inflated stellar models with radius anomalies equal in magnitude to those observed in nature and compared the resulting lithium abundance to the Pleiades pattern. We found fantastic agreement between the predicted upper envelope and the upper envelope of lithium abundances of cool stars, strongly supporting this theory. We further showed that this mechanism predicts the spread seen in 6 other young clusters. We conclude that this effect almost certainly causes both the lithium dispersion on the zero-age main sequence and the correlation between rotation and lithium abundance. Third, old clusters show clear signs of additional non-convective lithium destruction occurring on the main sequence. Several mechanisms have been proposed to explain this additional destruction, but none have been definitively proven. In order to assist the testing of these mechanisms, we have produced the most precise measurement of main sequence depletion to date. We do this by subtracting a theoretical lithium pattern from 2 empirical main sequence patterns, the Hyades and M67. This removes the lithium destruction occurring on the pre-main sequence, which can vary from cluster to cluster due to metallicity differences, and leaves behind the raw lithium anomaly that develops on the main sequence. We found that the amount of extra mixing is mass dependent, such that lower mass stars deplete lithium faster on the main sequence than higher mass stars. This result can be used to anchor future mixing calculations and test their predictions. Finally, a lithium dispersion at fixed mass is observed in the solar analogs of many old open clusters. This dispersion almost certainly develops on the main sequence. Previous studies have been unable to measure the magnitude of this dispersion because strong pre-main sequence mass trends severely contaminate any measurement of this quantity. With our calibrated pre-main sequence models, we can subtract out these mass trends, leaving behind the true dispersion. We find that dispersion is a general feature of lithium patterns at all masses and ages, and develops as early as 1 to 200 million years in some open clusters. This suggests an early origin for this feature, qualitatively consistent with the expectations of rotational mixing models. The largest spread of rotation rates occurs in the first couple 100 million years of cluster lifetimes, so the largest degree of differential lithium depletion would be expected to occur then in this paradigm. We also found that different clusters show different magnitudes of dispersion at fixed age and mass, implying that true cosmic variance may be impacting lithium patterns. This could also be explained by the rotational mixing paradigm if cluster initial conditions impact their angular momentum distributions. In summary, we have reconciled standard stellar models with observations in the solar analog regime, proposed and validated an explanation for the lithium dispersion in young cool stars, uncovered strong mass trends in the rate of main sequence lithium destruction, and shown that dispersion is a general feature of cluster lithium patterns. For more information, please see the preprint of our paper which is appearing on arXiv. Thank you for watching.